now. And if you're trying to watch our program on revolution.radio, you probably didn't hear it today because the Studio B server is moving to a new location and it will not be active for another 2 days. So we're recording this on Skype without our Studio B server, and we're simply going to be playing this tonight on Magnetic Reversal News.
At 8 p.m. Mountain Time, 10 p.m. Eastern.
Yeah, which no one can hear, so they won't know that that's anyway.
No one can hear that?
Yeah, we're not on the radio.
Oh, right.
All right, we got a great show for you today. We're going to be talking about two amazing topics, and we're not constrained to time, so we can go as long as we want here. The first, a paper coming out yesterday about the type and nature of the asteroid that killed the dinosaurs, suggesting that it was a carbonaceous chondrite from far beyond Jupiter. We'll get into that. We'll talk about the different types of meteorites. We'll also talk about the fact that these science writers don't even know what they're writing about. They talk about one article says that this is the most recent mass extinction, which means they know nothing about geologic time. So we'll break that all down for you, and you're going to come away knowing more than most people on Earth. In the second half of the show, we're going to be talking about more deadly things that come from space. But these are not necessarily impactors in the sense of an asteroid. These are impactors in the sense of major solar storms and solar storms that could, in fact, end modern life as we know it. And if you've been watching the show for a while, you know that what they're called Miyake events. So we'll talk about those.
Isn't it fascinating how, we live on this planet believing that everything's relatively stable, and yet we're constantly at risk from impactors, whether they be meteors or asteroids or Miyake events or whatever. I mean, things are so tenuous in one perspective, and yet there's this incredible proliferation of life here. I find it fascinating.
Well, what's more interesting, I think, is that in our lifetimes, we've seen such a shift as far as the way science has been going. But the reality is that no one in the classroom is being taught about the nature of the Earth, which is very chaotic. This all stems from the beginning of the discussion of geology and paleontology. So let's take a little ride. First, let me share the screen, and we'll tell you a little story. About 200 years ago was the very beginning, the infancy of geology and paleontology on Earth. The science itself is less than 200 years old. And it's just the idea of plate tectonics and the dynamic surface of the Earth is just a few decades old. And at the very beginning, they had to choose between catastrophism and not catastrophism. And they picked the non-catastrophism, which is called uniformitarianism. And that is the straw that broke the camel's back.
I mean, it's interesting, right? Because that choice was probably based on a psychological factor, right? Like uniformitarianism is much more comfortable because it allows you to believe that everything's stable and things are as they always will be.
Right. And when they were using Occam's razor back then, or their version of it, they all concluded that, well, yes, if we use the processes happening right now at this moment, we can use them to explain what we see in the past. That's all that they were suggesting. The only problem with that is very rapidly, people like in the early 40s, like Hibberd, started to find bone beds and these other catastrophic events that don't line up with uniformitarianism, and there is no way to explain it. And let's talk about the Dino killing asteroid that's pictured here, which created the Chicxulub crater. It was only in 1980, less than 45 years ago, that someone suggested that the extinction of the dinosaurs was due to an impactor, and the entire scientific community laughed at them.
Yeah. Right. This was the discussion when we were kids
Yeah.
about what happened to the dinosaurs. Was all of this controversy about whether or not this impact was what wiped them out.
Right. There was like the main argument was volcanoes. There was lots of volcanic eruptions that darkened the sky. And that was the consensus at that time. But someone said an impactor. And it took 11 years since that suggestion till the first shred of evidence came to light. And that was in the form of, I guess the science got better, and they were able to isolate the platinum series elements in this crater. So someone was able to see it from satellite, I guess, or infer it, maybe LiDAR. I don't know how I've
Found
looked
the
into
crater.
it before. I don't remember. Go ahead.
Yeah. How they found the crater. Is that what you're talking about?
Yeah. And so they found it, and they went and took some samples, and they were able to isolate these platinum element. And then it was confirmed after that worldwide in several other areas that 66 million years ago, a cosmic event occurred that deposited these platinum elements. And now, so the science has gotten even better. Yeah. And now what we're talking about today is where did this gigantic 10 to 15 kilometer wide asteroid come from?
Right. But even more than that, like this paper that we're going to talk about, it also eliminates the possibility that some of the chemical signatures were caused by, let's say, volcanic activity. It basically eliminates that hypothesis.
Yes. So this is again, straw in the camel's back, or the nail in the coffin, that eliminate, well, there were volcanoes going off here.
Yeah, right. But this specific paper, which talks about the ruthenium isotopes found, eliminates that it could have been a cometary impact, like a cometary body that it's actually an asteroid, and that it can't be volcanic either.
Right. And in this article by CNN, they call it a mud ball.
I know that annoyed me so much. It's like,
far from the truth. It is not, in fact,
dumb it down. It's so it sounds so stupid, and I find it very insulting the way they wrote this article.
It is CNN.
Right. It's not really surprising, but
the clown news network.
Yeah.
Well, so we'll come over to Science. They have a much better article on it the day before it was released. So clearly they had the preprint.
Yeah.
Dino killing asteroid came from beyond Jupiter. And that's basically the synopsis of the entire paper. But this paper takes on so many assumptions.
It does. It does.
What we can glean as scientists is the specificity of the type of asteroid that hit us.
Right.
So here's the paper. It came out yesterday. Ruthenium isotopes show the Chicxulub impactor was a carbonaceous type asteroid. What the heck does that mean? Well, there are three main classes of meteorites that hit Earth, or asteroids. The meteorite is the object that hits, that we can hold in our hand. The asteroid is the meteorite moving through space. So let's get that clear. They're the same thing. An asteroid is a moving meteorite.
Right.
So the three main types that we've collected on the surface are stony iron, and iron. And they're really, really different types of rocks.
Not mud balls, rocks.
No, they're rocks. And they all contain metals. Right. So these are really high temperature, weird space rocks, which they are. They're meteors. They fly around space. They're formed in space. And here, take a look at this graphic. They probably are all parts of what were originally stars and planets.
Right.
And so the cores of these planets break down and eventually become 10 to 15 kilometer carbonaceous chondrites that strike Earth and kill the dinosaurs. So there's different lithologies. These are all assumptions onto where they're coming from and a planet or a star. But it's a pretty good starting point and a pretty good theory. And there's no better theory to suggest that it's any different than this.
Right.
But I would suggest that the chondritic stony meteorites are definitely from a planet. because they're the only ones that contain high amounts of carbon.
And they're the most similar to what we find terrestrially.
Right. So they're just like a planet. So if you took a planet in a catastrophe and smashed it all up, melted it, and threw it into space, it probably would look like this.
Mm-hmm.
They also suggest that these chondritic stony meteorites are what formed Earth in its first billion years and gave us all the carbon and water.
Mm-hmm.
Because the amount of chondritic meteorites that hit Earth today are 5% or less, which is one of the assumptions that they think, because some of the larger impactors on Earth we've proven are from these chondritic meteorites.
Mm-hmm.
So they were far more abundant billions of years ago than right now.
Yeah.
Now, I don't know what that means. Do you have any ideas?
I mean, there could be a lot of different reasons for that, right? I mean, this paper relies on the accretion model of our solar system formation. And that then sort of says, well, that's why we find that these types of asteroids come, or meteorites are from the inner solar system, and these are from the outer solar system. But there's lots of other models that you could work with here, most of which are not accepted by officials, the typical narrative for science. But, you and I have talked many times about potentially the motion of solar systems being that helical motion, that we're moving through space, and perhaps we're experiencing more interaction, let's say, with other solar systems, right? And perhaps we were experiencing an interaction with another solar system long ago that contained more chondritic meteorites, right?
Right, and they assume these chondritic meteorites come from beyond Jupiter.
Jupiter, right? Which I think is, I mean, I have not. Okay, now, granted, when this paper references stuff like that, it does it does give notation references, and I haven't read those references.
Yeah.
So apparently, some people have done some work to say, okay, this kind of meteorite would come from beyond Jupiter, and this one wouldn't. I had not having reviewed that. I don't know how valid.
Yeah.
That
So
is.
what they find, the astrophysicists find, is that beyond Jupiter, they have isolated some asteroids that exist that have the chemical signature of chondritic, these high carbonaceous chondrites.
Right.
And they find them past Jupiter when they look at them. Almost all of the objects we find inside Jupiter's orbit, so Jupiter towards the sun flying around, are all these types of iron, calcites, or other meteorites that are not the rocky type. So
Well,
there's
so
very
here's
few
another
stony. Go ahead.
There's another potential explanation, right? So if we look at this through the lens of an electric universe, an electromagnetic universe, it could be that the composition of certain meteorites and where they're located is based on the electromagnetic dynamics more than anything else, not where they were initially formed.
And also you can add in the fact that things like the asteroid belt all contain similar material. So a chondritic object might have broken up outside the orbit of Jupiter into a billion pieces a long time ago, and that's where they stay in their orbit. Mm-hmm. And every now and again, one gets knocked into the inner solar system, the sun sucks it in, and sometimes they hit Earth.
Well, it's funny, too, because this paper also talks about how the vast majority of asteroids are found in the asteroid belt. And so the ones that are from the outer solar system would have had to have migrated there at some point.
Yes.
So from that to then make these assumptions about where those asteroids where they originated, seems kind of silly to me.
Right, but we do now know the composition of the asteroid. It was a carbonaceous chondrite. It was similar to big impacts on Earth billions of years ago, and it appears to be the last big impact from a chondritic meteor, one that is a mass extinction event since then. So no chondrites have hit us for 66 million years.
Right.
Well, and big ones anyway. 5% of small asteroids are still chondritic.
Right. Right.
It could be pieces of this Chicxulub.
Right. Could be.
Yeah.
And Chicxulub was huge, right? It's like estimated between 6 and 9 miles wide.
Yeah, 10 to 15 kilometers.
Yeah. I'll just say too that despite the assumptions in this paper, thankfully, the critical information and understanding that comes out of this does not depend on those assumptions so much, which is great.
Yeah.
I find them to just be kind of extraneous and interjectory, and they just don't need to be there.
So what's also interesting, I don't know if you know, but Chicxulub isn't the only crater that dates to 66 million years ago.
Mm.
The Nadir crater off of West Africa, this is in 2022. They were doing seismic studies. They were doing sea floor spreading analysis, and lo and behold, they found an 8.5 kilometer wide crater that dated to 66 million years ago.
Well, that's really interesting for a couple of reasons. I mean, it would obviously suggest that there's something going on in our solar system that's much bigger, right? If we get two big impacts in the same sort of time frame.
This is like a small chunk it was dragging.
Okay, yeah, right. So it could have just been like a piece of Chicxulub.
The crater created by Chicxulub was 100 miles wide.
Yeah.
And so this is only 8.5 kilometer wide structure.
Right.
So it's a piece it drug in.
It's a remnant. Yeah.
Yep.
Yeah. But it also helps explain why you find, for the Cretaceous Paleogene boundary, why you find the platinum group elements all over the globe. Now, granted, it was a huge impact, right? So you're going to get a incredible, what's the word I'm looking for?
Nuclear winter.
Yeah. I mean, you're going to get the spread of these particles all over the globe.
So the Chicxulub impact alone, take a guess how many Hiroshima bombs it was equivalent to.
Oh, I don't remember. I've seen this stat before, but
1 billion. So it's a big boom.
Right. But if there were also little chunks that were impacting elsewhere, it would just, further lend more explanatory power as to why the platinum group elements appear globally, as well as the associated ruthenium isotope, which we'll get into.
Yeah, well, I was just going to close it up on that and jump into another topic. The ruthenium and them isolating this isotope is what eliminates volcanic eruptions as the cause of the mass extinction, because ruthenium only comes from space rocks. There's very little on Earth.
Right.
And what's on Earth, probably because there's so little, probably came from space rocks.
Right. But what this paper does is it analyzes the ruthenium isotopes of different, let's say, impact craters, as well as the Cretaceous Paleogene boundary, and compares and contrasts them, and you find, specific isotopes essentially for specific events, and so that allows you to eliminate other causes of the deposition of that ruthenium isotope.
Beautiful. This is a beautiful transition. So they looked at a mass extinction impact 36 million years ago. They looked at one 470 million years ago. And then the ancient ones I keep talking about, 3.5 and 3.2 billion years ago.
Mm-hmm. Yeah.
But what the articles and none of them talk about is the fact that the geologic record exists.
Mm-hmm.
So all these impactors are falling on one of these lines. And all of these lines are mass extinctions.
Right.
So to say that this one 66 million years ago is the most recent mass extinction is so incorrect, it's almost mind-boggling.
Mm-hmm.
Because every one of these boundaries is when all the animals below it disappear and everything above it is completely new and weird stuff.
Right. I mean, that's what defines, it's the reason why we have these geological era transitions, because all of the life on Earth changes, basically.
Which means what happened?
Which means that there was an extinction event.
Or you could call them mass speciations.
Sure.
And so these all coincide with a major impact, which changes here. Wait for this one. The Cretaceous Tertiary, which is now the Cretaceous Paleocene, the extinction of the dinosaurs, there's good evidence that below the boundary, when dinosaurs existed, the gravitational field of Earth was very strong and may have pulled this baby right to us.
Right.
And so after it hits, it rings our bell, changes our orbit, and the gravity's different and stabilizes.
Right.
And then you can get mammals on Earth. It's mind-boggling. That's just one boundary. Every boundary you're seeing here is a significant change.
Well, not only that, and we've talked about this in detail on another show when we talked about panspermia. We talked about how, believe it or not, certain organic life can actually survive in space, and that may also include genetic material, right? So the idea is that we're regularly getting new genetic material that's raining down on Earth on a regular basis, and if the conditions change to make that the life associated with that genetic material possible, then it very well may show up. And so it's not just the extinctions, but it's potentially all of this other material on Earth that can create different life forms.
Yes, exactly. And different cosmogenic environments. We're talking 500 million years that we have life in the form of fossils.
Mm-hmm.
What can occur cosmogenically in 500 million years? We move so far through the Milky Way. In 500 million years, we go through several of the spiral arms.
Right. Right.
And those are all these big mass extinctions. So the Paleozoic is a spiral arm. The Mesozoic is a spiral arm. The Cenozoic is a spiral arm. These are all completely different environments. This middle one was hundreds of millions of years of giant dinosaurs and lots of gravity. During the Paleozoic was the dawn of fishes. This is when all the life in the oceans began. The first plants come out on land, and then all of the oxygen shows up at the end of the Paleozoic because the entire Earth is covered with these amazing forests.
Mm-hmm. I mean, from a spiritual perspective, this is really kind of beautiful, right? You have this cycle of death and destruction, and then life and new origins, right? And it's like if you want to talk about, the idea of God, like exploring itself through every possible expression. Well, this is one way to do it, is to regularly destroy and create new things, right? It's like it's the destruction of, it's the cycle of life and death that allows all of this infinite expression to occur.
Yeah, and the chart we're looking at here is a beautiful way to see it in a very long geologic timescale. This is 500 million years, starting with the Cambrian, and you can see all the mass extinction events on the left here. They draw all the extinct bones of these animals. Mm-hmm. So there are dozens of mass extinctions at this scale. But if you start to hone it down into more modern scales, there are hundreds. There are literally thousands of mass extinctions at every scale.
Right.
And the last one just happened 12,850 years ago.
Right.
And almost no one on Earth knows that.
Right.
Prior to that mass extinction, there was a Miyake event, and we'll get into that in just a minute.
Yeah. Can you go back to the previous image for a second?
Yes.
I find it very funny that they have this like truck at the top. like that's some like new life form or something.
It's got a big nautiloid in it too.
Right. Well, it's also right. A nautiloid, yeah. And then it's also funny just because, it resembles a truck from like the 30s or 40s.
Exactly. And so that is the actual surface of the Earth. The surface we're living on currently is the surface that was created 11,700 years ago during the Holocene.
Yeah.
When the sea level rose and we've become stable, the surface of the Earth is now that boundary still. Mm-hmm. And in the last 11,000 years, there's some dirt and some deposits that are on that surface, but not much.
Yeah.
That is the scale of geologic time. It's absolutely mind-boggling.
Yeah. And from this perspective, from the very wide perspective of looking at geological time, what I was saying earlier about death and destruction and new life, I mean, it is quite beautiful, but obviously if you're inside it and living during a mass extinction, it's not so pretty.
Yeah, and there's another way to look at it too. We've been in the Cenozoic now for millions, 66 million years since the dinosaur extinction. When does our epoch end? And what
Right.
new animals that are completely unknown will fill the next void?
Right.
That's weird.
No way to know ahead of time.
Because the Mesozoic, the time of the dinosaurs, lasted for almost 200 million years, 190 million years. That's a long epoch. And the Paleozoic also about that long. So we're just in the dawn of our epoch, the beginning.
Right.
They last 200 million years, and we're only 66 million years into it.
Right.
Wow.
Right.
And so during the Mesozoic, the dinosaurs went from 4 inches high to Tyrannosaurus Rex at the end.
Mm-hmm.
What's going to happen at the end here?
Right. Right.
Will we be giants in 120 million years?
It's anyone's guess. It's just a giant experiment, you know?
All right, so you can be a doomsdayer or you can learn about the science and understand what happens. Let's talk about the threat of Miyake events, and let's make some of our own conclusions and predictions by the end of the program to blow your mind. Because, like it or not, it's coming back again. Whatever it may be, they happen every 500 to 2,400 years. So the big question is, what are the superstorms from space that could end modern life? And this article was just sent to me by Willie Soon the other day. Now, what I find fascinating is the history of the discovery of this. So you got dendrochronologists that are looking for stuff. They don't know what they're looking for, and they stumble across a carbon-14 spike in a tree ring. Then they corroborate it around, and they're like, wow, what is this? And the conclusion is it's a type of, well, first, in the early days, they were like, it's a supernova from a faraway distant star.
Right. It couldn't possibly be our star. That couldn't
Yeah,
happen
like no
here.
one thought about the big burning thing in the sky. The global warmists certainly don't think of that.
Right. Our star is nice. It doesn't flare. It just stays constantly warm. That's it.
Yeah, and this brings us back to uniformitarianism and catastrophism. And catastrophism is the way. Just like permaculture is the way, catastrophism is the way.
Yeah, yeah. Well, like the uniformitarianism as applied to the sun, right? It's treating the sun like as if it's a constant variable. As we've discussed many times, the sun is not a constant variable, but the current, climate science treats the sun as if it's like not even important in the equation.
But
like,
if you
like it's
look
not
up
even
what our
there.
sun is, it's by definition a variable star.
Right. Right. Right.
It varies so widely in an 11-year cycle and a 22-year Hale cycle that it literally changes the luminosity and the amount of energy hitting Earth on those scales.
Right.
So the biggest superstorm we know about in modern history is the Carrington event, and that's kind of on the cusp of what we call modern.
Right.
In 1859, we barely had anything electronic, a few wires here and there. And but the Carrington event was one of the largest superstorms we've experienced. But you and I have discussed on this show that it's not unique, right? We've got the 1989 Quebec storm that caused a blackout, 2004 storm. We just had one this year. None of them were at the scale of Carrington.
Right. And yet Carrington as compared to a Miyake event is tremendously small. So in dendrochronology, the carbon-14 spike that you're going to see, Carrington doesn't even register because this is hundreds of times less than what we're calling Miyake events.
Yeah, and that is the most conservative estimate. So what you do is you take a Carrington event and you times it by 100 at the minimum.
Right.
There are estimates this could be up to 2,000 to 3,000 times stronger than the Carrington event, especially the most recent Miyake event discovered, which coincides exactly with the bowling alley rod cooling. So at the peak of the warming was 14,300 years ago, and that's when this event occurred, and we rapidly cooled down into the Younger Dryas period.
Right.
And when I looked at the other temperature graphs of the Holocene, all of the Miyake events correspond to a peak in temperature, and after the event, the temperature drops.
Right. That's very interesting.
Very interesting. So do you want to give a little background, any more to discuss on the background of Miyake?
Well, just another one of the things that this article rightly points out is that one thing that is not clear is like if a Miyake event is kind of a isolated event, or is this something that occurs, let's say, like over the span of a year?
Yeah,
we don't
go
know
over
that.
a paper which was able to pinpoint the duration of these events, and it lasted between like 8 months and over 2 years.
Right. And then what does that mean for, let's say, organic life on Earth in terms of radiation? I don't know that we know the answer to that. I mean, this article claims like, oh, people in the past wouldn't have even
Noticed
this except for aurora, but it wouldn't have affected their lives. But I'm not sure that that's true. In a sense, like it wouldn't have affected their lives in the sense that it certainly would affect our lives today because it would have massive technological repercussions. I mean, absolutely no question, the civilized world as we know it would be destroyed, right? All of the
they
satellites would be
literally
gone.
correspond to the Dark Ages.
Right. Right.
The coldest time on Earth in the Dark Age happened after the Charlemagne event.
Right. So that's another factor, right, that this article doesn't take into account at all. You're seeing the correlation between a massive temperature drop, therefore a dark age. That obviously that's going to affect people on Earth whether you have technology or not. It's not just about the technology, and I think that's a very mistaken idea.
Right. So let's go over the known events, and we're going to link you all the papers to everything we talk about below the video so you can do your own research, homework, or share it with others. This is an abstract, but it pretty much sums up the state of all the knowledge up till this year. The most recent discovery was the one I was talking about, 14,350 years ago, the strongest Miyake event known. And then we've got an event 7176 BC, 5259 BC, 775 AD, 993 AD.
Mm-hmm.
Now, the events of 5410 BC, which would be 7,410 years ago, 1052 and 1279 AD are less pronounced, and they require some confirmation. But the other events are confirmed.
Right.
But I would lean towards all these events are probably confirmed.
Sure.
So there's a periodicity of these events between like 500 and 2,500 years. The last one was quite a while ago, so we could be in that Miyake window.
Right. The other thing that's interesting about this, I keep thinking about the correlation between the temperature drop and a Miyake event, and I wonder. I mean, I don't know what the causal agent would be, but you could surmise that if you're having a Miyake event, you're having a huge quantity of particles hitting our atmosphere, which changes the chemistry in our atmosphere.
You're going to strip the ozone immediately.
Yeah.
All of the ozone will be gone.
Right.
And so how does that cause cooling? Anybody's guess.
Right. But there's going to be a whole domino effect.
Listen, 1,000 times more cosmic rays. How many clouds are you going to nucleate?
Right.
The whole planet may get cloudy.
Right. And so, yeah, like within that, you're going to have a whole domino effect of chemical and nuclear synthetic reactions in the atmosphere that is going to change things dramatically. I mean, that's how we get carbon-14 spikes in the first place. We get particles hitting our atmosphere, interacting with nitrogen, and that's what creates carbon-14.
And then it rains down on us.
Right. And ends
up taken up by the trees in their rings.
Right. Which is interesting too, because last week we mentioned that there's a difference in how plants uptake certain isotopes of carbon. So, for example, plants don't readily uptake carbon-13 very well, but I guess they do uptake carbon-14 better. But that means that you also need to look at that when you're looking at these carbon-14 spikes in dendrochronology, because they may also be affected by how readily trees take up carbon-14.
Absolutely.
You know?
All right, so let's walk it through with you. Let's go to the strongest Miyake event known. That goes back 14,350 years. That's actually 400 years, because most of this starts with the 1950 data set. So you got to add 50.
Right.
But if you come look at pre-Holocene data and the older Dryas, the IACP, and then finally the younger Dryas event here at 12.8, this is the extinction event. This is the impact. Boom. But 14,400 is in this dip here. And shortly after that, you could even put it here, 14, what did I say it is? 350 or 400. So that's right in this dotted line, the second peak of the bowling. And then it gets cold straight after that.
Yeah.
So that's the first Miyake event. It happens right here.
Yeah.
It's followed by hundreds of years of cooling.
Right.
Tries to warm up, then something happens, it cools again.
Yeah.
Tries to warm up, then we get impacted, and then we go into that 1,300-year ice age. Okay, so that's the first. Go ahead. What do you want to say?
Oh, I was just going to say that is also interesting from the perspective of, let's say, everything that we've looked at that Göbekli Tepe might be indicating or pointing to, that perhaps there wasn't one impact, but multiple impacts in this time frame. You know, the Göbekli Tepe does seem to suggest that there's, let's say, a cometary body, perhaps, or associated meteorites coming from a particular place in the sky. Like something, you know, there's something that happened. Like it's like clearly pointing to, like, look, something happened at this time.
Yeah,
but maybe it is also pointing to all of this.
If the impactor here at 12.8 came into our solar system around here and started moving close to our sun, it could have caused the Miyake event.
Right.
And that would cause the cooling, knock the bolide into a different orbit. Eventually it hits us after a few thousand years of getting closer and closer.
Or there's multiple pieces that are hitting us, you know.
Definitely, as it would suggest, there are multiple things that come in.
Yeah.
But, okay, so what's the next date? The next date is 7176 BC, which would be 9,200 years ago. So if we go back 9,200 years ago, that puts us at this peak right there.
Yeah.
And what happens after that?
That's a massive drop.
About 3C.
Yeah. In a short period of time, too.
It's all about 300 years, all of these drops.
Yeah.
And then it warms up again. All right. Next one. 5259 BC, which is 7,300 years ago. 7,300 years ago is this peak exactly, right up here. And after that peak, 7,300 years of Miyake event, and then the temperature drops 2.5 C. And okay, where is it? Then we've got the Charlemagne event. We've got 775, 993 AD. Do we have any other ones?
It's hard for me to read this. I have to blow it up every time.
When we get up to that data, it's all compressed right in here.
Right.
So the Charlemagne event and all those events happened during the Little Ice Age. In fact, this peak may have been thwarted. This rise up may have been thwarted by the Charlemagne event and kept us in the mini ice age.
Yeah.
Now, correlation isn't causation. We're just putting data points on a graph.
Sure. I mean,
it is compelling because we didn't find anything like exactly opposite.
Right. Right. I mean, you have to ask the question in both directions, right? You have to ask about the temperature increases, since certainly, 10,500 years ago, I don't think we can claim that human beings were causing massive global warming of almost 4 degrees. But like,
Every
you have to ask
thousand
the question in
years,
both directions. You have to
every
ask about the
thousand
warming
years,
and the
we burn
cooling.
too many fires. See,
Right.
during the Minoan warm, all the Minoans had babies, and then the temperature went up.
Right. I mean, it's funny from the perspective of, if you're in that camp, you're going to look to explain all of the warming events and find some way to blame it on humans. But what about the cooling events?
That are
Because there's
just as
plenty of them.
drastic and immediate.
What?
They're just as drastic and immediate as the warming events.
Right. Right.
And so, what do you think is going to happen after the modern warm period peaks?
I
According
guess
to the
that's
global warmists, it's going to go straight up infinity.
straight to hell.
But clearly, based on this 10,000 years of data, it is actually going to go straight down.
Right. But again, I mean, as we've pointed out 1,000 times, like, look where we are right now, temperature wise, versus where we've been. It's like, oh, I'm sorry. The state of science today is just embarrassing. Most of it, not all of it, but
Yeah, this is a bigger expose with a different scale on the side. They shrunk it down so it's not as steep, but it goes all the way from the warming at the end of the Younger Dryas. It shows you the temperature rising a ridiculous amount in less than 1,000 years, staying extremely hot, up to 3 degrees C hotter than today's hockey stick. But most of the last 8,000 years warmer than today.
Yeah.
But it's the hottest year ever.
Right. Right.
All right. What else? Do you want to beat this with a dead horse? Or are we good? What's the conclusion?
Well, human beings are certainly not in control of the climate. That's for sure.
No, and there is an imminent Miyake event headed our way.
Yeah. Well, we don't know how imminent, right? Like, it's not like we can't make a claim like it's on some very regular schedule, like every 12,000 years, but it is a somewhat regular occurrence. We don't know that we do not know if there is a cyclic pattern, partially because there's probably a lot of these Miyake events that we haven't even uncovered yet, right? This is relatively new research as far as people finding the evidence for it. So there's probably quite a lot more since we're seeing it this much as it is.
Right. And the more recent you get, the higher resolution we have. We actually have a Miyake event in 775, 933, and then we have one at 1052 and 1279. That's 4 in the last 1,000 years.
Right. And that's probably more telling than anything else. I mean, this article also rightly points out that in reality, for dendrochronology, the best we can hope for is a history of about 30,000 years.
Yeah, because that's all the wood we have in our possession.
Right. And that includes fossilized wood.
Right, because the oldest living tree is 5,000.
Right.
Yeah.
So, the data set is limited, and it certainly doesn't mean that you get good data over 30,000 years by any means, right? The data is still going to be limited.
Amazingly enough, that Corey tree they found in New Zealand was growing during the Lechamp magnetic excursion 41,500 years ago.
Yeah, that is interesting.
So as our technology gets better, I think we're going to get better and better data.
Yeah. But it also depends on us finding specimens like that have been preserved just due to some sort of random set of conditions.
Right. And we don't even need a Miyake event to end modern technology. So just a Carrington level storm and science comes to a halt for quite some time.
Yeah. Yeah. Everything comes to a halt, really.
Yeah. A lot of people are going to be focusing on growing food.
Yeah. Yeah. Well, the people that survive and remain, I mean, and figure out that they need to figure out how to grow food instead of stealing it from other people, let's say. I mean, that's the biggest threat, in my opinion, is this to live with this idea again that everything's stable and hunky-dory all the time, uniformitarianism, when in reality we have catastrophes on Earth all the time. It just hasn't happened really in the course of most of recorded human history, as far as we're aware. So, I mean, the total dependence on globalist systems for food and everything else, that's the real danger, right? Because most people, well, I don't know if that's most people, but probably most people don't know how to grow food. So to me, the biggest danger is from people who are unprepared
Yeah,
or
but there's
unskilled.
pockets of freedom. Like every human in Uzbekistan in the foothills is growing their own food.
Right, right, which is why I kind of stumbled over most humans. But so, I mean, but you could, because I don't know exactly how it breaks down, but I think the majority of the population lives in cities.
Yeah, but that's only 15% of the population living in the modern world.
Okay, so that's not most human beings living in cities.
Well,
You
that
know?
15% of the population are living in cities in the modern world. The rest don't
Oh,
even
okay,
have
I see what you're
internet.
saying.
Yeah.
Right, right, right.
Yeah. So there's very few people living in the modern world that are self-sufficient. They estimated as that 15% that's in the modern world, only 1% is self-sufficient.
Well, and then you add to that let's say we have a Miyake event that destroys civilization as we know it. Obviously, from the data that we just looked at, that's also going to change the climatic conditions tremendously. So even the people who are self-sufficient and know how to grow food are going to have to adapt to a whole new set of conditions. Which
Welcome.
it helps if you already know how to grow food, right? And you know
Yeah.
how to observe conditions and how to change what you're doing to make it work and be successful. Obviously, that experience will help. But
Right. And
in another respect, everybody is back at ground zero.
you get more chilling hours for your apples.
Yeah.
Guys,
Another really good reason to save seeds.
we're not on Revolution Radio today because they're moving their servers. I guess it's been a big upgrade. They hit their goal for fundraising, but that doesn't mean you can't support freedom of speech. Come over to Revolution Radio, become a Patreon, or do a one-time donation. And if you want to listen to us next week, we'll be in Studio B here, noon Mountain Time.
Yep.
Great show.
See you tonight. This is tonight.
This is tonight. And that is a boom. This is tonight.